We're going to look at some problems that have to do with identifying graphs of trigonometric functions. So I wanted to take a look at some of these trigonometric functions first. What you see here is the sine function. So this is a graph of y equals the sine of x. And you know that the sine of 0 is 0, so the point 0, 0 is going to be on here. And then think of the sine function on the unit circle. As it goes up towards pi over 2, it rises to 1. Then as it approaches pi, it falls back down to 0. As it approaches pi over 2, it goes down to -1. And then it comes back around at 2 pi to 0. So here's 2 pi. And that whole trip from here to here, we call that the period of this function, because afterwards it just repeats itself. Both that direction and that direction. It keeps on going on like this for every period of 2 pi. So that's the period. There's also something called the amplitude here, and that's how high it gets. And for your basic function, the amplitude is 1 here. It goes up to 1, it goes down to -1. So that's y equals sine of x. You can get slightly more complicated graphs of sine. This one here, you'll notice the amplitude has been changed. This is actually y equals 3 times the sine of x. So if you put a multiplier out front, you're going to change the amplitude. Now it's going up to +3 and down to -3. The period is the same length. It still goes from 0 to 2 pi here, but the amplitude has been changed. And if you were to put a 1/3 in front of the sine x, it would only go up to 1/3 and down to -1/3. So that's how to change the amplitude. Here we've actually changed the period. And this is y equals sine times 3x. So we put a multiplier on the x here rather than on the whole sine function. And you can see what we've done here between 1 and 2 pi is we fit in 3 whole periods. If you were to put a 1/3 in front of that x, you would stretch it out, and it would take actually 6 pi to get 1 period in there. Now this one is slightly more complicated. This is y equals sine of 3x plus pi over 4. And what we've done here, we're altering the period with multiplying by the x here. So we've got 3 periods in that 2 pi length. But we've also done what's called a phase shift by adding here. And you can add or subtract inside the parentheses here. The value that you add is going to move the whole function this way by that amount. So we've shifted this pi over 4 in that direction. And you can see here's our 0, and here's our 0 that's been shifted in that direction. So we've got the amplitude, we've got the period, and we've got phase shift. Now this is y equals cosine x. And it looks very much like the sine function, except that instead of starting at 0, 0, it starts at 1. But pretty much everything else is the same. The period is, again, 2 pi for your basic function. Goes from 1 down to 0 at pi over 2, down to -1 at pi, back up to 0 at 3 pi over 2, and up to 1 at 2 pi. And of course you can do the same kinds of amplitude adjustments and phase shifting with the cosine function. See this big long waveform here? This is actually 2, you can see the amplitude, it reaches up to +2 there, times the cosine of 1/3 x. So this is going to have a complete period taking place in 6 pi rather than 2 pi, which is why we can't see the complete period here because our graph's not long enough. And this is minus pi over 4, so it's actually been shifted 1/4 that way. So here's our top of our function, and it's been moved from the 0 pi over 4 in that direction. All right, so let's look at a couple of problems. Here we're being asked to find 3 times the cosine of pi over 4 times x plus pi over 3. So we've got a couple of things going on. The amplitude has been changed. So let's look at our graphs here. Now it looks like A and B both go up and down to positive and -3. C doesn't look like the cosine graph. Actually, that's a graph of the tangent function, and we'll get to that later. And then, of course, it could be D, I suppose. So we'll have to rule that out. Let's look at what's happening next here. We have a multiplier, pi over 4 times x. That multiplier is between 0 and 1. So although it's pretty close to 1, 3.14 over 4, so it's just going to stretch it out a little bit. And then we're phase shifting it that direction, pi over 3. Now remember, the cosine starts at 1, or in this case 3, because there's a multiplier there. So the one that this graph actually matches up to, or this function matches up to, is this graph here. You can see it's been shifted a little bit in that direction. That corresponds to that pi over 3 there. And it's also been stretched out a little bit. Now, if you wanted to verify that this is actually the right one thing I'd recommend is plugging in some value for x and actually cranking out the numbers and seeing where it falls on the graph. You'll find out that it's actually b here. All right, let's look at one more. This one is the graph of y equals the sine of 3x minus pi. Now remember, when you put a multiplier here on the x, what you get is 3 periods for every 2 pi. And our amplitude here, there's no multiplier, so the amplitude is going to be 1. So that leaves b out, because the amplitude on b is clearly greater than 1. On a and c, well, it looks like the amplitude is 1 for both of those, although this one's been shifted down below the x-axis. And that would happen if you were to subtract 1 outside of the parentheses, but that's not there, so it's not going to be c. So it could be either a or d. Let's look at a more closely. We know that the sine starts on 0, but this has been shifted by pi in that direction. Well, sine is also 0 at pi. So the resulting thing is that instead of starting at 0 and going up, it starts at 0 and goes down, and that fits with this graph. And then we do have 1, 2, 3 complete periods between 0 and 2 pi. So it looks like this is the correct answer for the sine of 3x minus pi. So that's a little bit of work with identifying sine and cosine graphs.